right, thank you very much, Rob. Yeah, so like you said, this is the third talk in the series of advanced propulsion. And I'm going to specifically focus on some implications and concepts derived from special and general relativity. And so a lot of this stuff, it's very fascinating, but you should take everything that's being told to you by me and also by other people when it comes to this kind of application with a grain of salt. And we'll get into that because this really gets to a point in our understanding of the natural world where we're at the fringe of understanding, and where the connection between relativity or the theory of space-time and the theory of quantum mechanics, the connection between them becomes really important. And as a lot of you probably know, this connection has not been made, well, somewhat in some cases successfully, but in general, it has not been made successfully. So I'll just start with some overview of the principles of relativity, and first with the special relativity, because that's the simpler case. And the two most important postulates of special relativity are that laws of physics are invariant in all inertial frames, and that light speed is invariant, meaning all observers, regardless how they move, they will always measure the same speed of light. And you probably heard this before, so you're familiar with these claims. What is important is that this approach so far is the most accurate model for all motions that we've been observing. Special relativity neglects gravity, and it only works for flat space-time, and we'll get into that. And the name relativity comes from the fact that there's no well-defined state of rest, meaning all the motion and observations are relative to the observer and how the observer moves in respect to other observers or other frames of reference. I'll give you an idea. So in special relativity, simultaneous events for one observer are not necessarily simultaneous for another. And that's like a classic example of what special relativity is. So if you look at these nice little trains, one person is standing here, the other person is in the train moving with a constant velocity. We have two lightning bolts hitting behind them and in front. The question is, will those two observers come to the same conclusion about where the lightning struck and at what time they struck? And to answer that, if we have flat space-time, often we use something called the space-time diagram or Minkowski diagram. And I want to show you that because if you've never done this before, it's unlikely that you're going to get all of the implications right now. But I wanted to show you this if you want to do some more reading on your own, because it's a very powerful technique to understand the implications of special relativity. So you have here a space line is x, and you have a time-like line. It's called the world line often. The speed of light times the time that is going by for the observer. And these diagonal dashed lines are the speed of light. And this black coordinate system would be our O frame of reference. So if we go back, this is the unmoving character. And then we have a second frame of reference, which is O prime, which is this blue coordinate system. As you can see, for the observer in the O frame of reference, so the guy that's not moving, for him, the space and timeline of the moving observers look different from his own. That's because they're moving relative to each other. And now you have two events. The lightning strikes A and B, one in front, one behind the person. And they are on these dashed diagonal lines because the photons coming from these events are moving at the speed of light. And now the question is, how do these two observers perceive those two events happen? And what is important here is that Euclidean geometry does not give a consistent answer. In fact, we need a space-time interval. This is the Minkowski space, and that was the great insight that actually came after the first formulation of special relativity, that space and time are not two separate things, but they're one and the same thing. And that's the insight that Newton missed when he derived his laws of mechanics, and that Einstein later had, that space and time are really one and the same thing. They are conserved, but individually they're different. And if we look closer at this event, the lightning strike A, then observer O that's not moving would say, the lightning strike happens here, and I see it at this time. That's what he would predict. But looking at the person that's moving, he would say, well, the moving person actually would see it at this time here, at this place. And you can see that this distance and this distance, or this time, and this time, and this distance and this distance are not the same. So the two observers, because they're moving relative to each other, would come to different conclusions. So we talked a little bit about this. Now, what happens? So maybe you've heard also what is inside of these diagonal lines here and below is what we usually call the future and the past. These are the light cones. So anything in here and down here can be or has been observed by our O frame of reference. Now, what happens when we move outside of this cone here, where below these diagonal lines or above down here, then we're in a range where something is moving faster than the speed of light, and it becomes causally disconnected from the rest of the things happening here. And in fact, it cannot influence and it cannot be observed by the person here, the frame of reference. From that notion, you also can define an event horizon. Anything that's in this area, you would not be able to observe. So the next question is, what would happen if you are not moving with a constant speed, but you're actually an accelerating observer? Well, in that case, what you can observe and what can influence you is constantly changing. So here we are an accelerating observer, so non-inertial, and these pluses and dots, they are, well, the dots is our trajectory, and the pluses are events happening somewhere in space and time around us. And if we're moving at a constant velocity here, nothing shifts, it's just moving down as time goes by. But as we're accelerating, you can see that some of these events move below the diagonal lines here, or they move from here above them. And that means that as we're accelerating, the events that can influence us and that we're observing actually shift in and out of our light cones. And again, this gives rise to the notion of an event horizon, but it's very interesting that as an accelerating observer, there's basically, as you change your state of motion relative to other things in the universe, the things that can influence you also keep changing. All of this, what we've talked about, the relativity of the location and the time interval between events, gives rise to the notion of the dilation effects. You probably have heard about that too, maybe through the twin paradox, that if somebody's moving fast, that for them time is going slower than for the observer at rest. It's a little bit simplified, but let's leave it at that. This dilation can be quantified with the Lorentz transformation, which is this factor here. And it's mostly just a function of the velocity at which one is moving divided by the speed of sound squared. Time is dilated in this fashion. So if somebody's moving fast away from me, then for me it looks like time for them is going slower. And at the same time, if somebody's moving away from me fast, or even towards me very fast, then it looks to me like the physical dimensions of an object are contracted. And again, if we would do this in a space-time interval, nothing would change. Then everything would stay constant. But if we're looking at those two quantities separately, then they change. And this dilation effects then plays into the derivation of Einstein's most famous equation. I just wanted to show this. So he originally derived the kinetic energy of a moving body as this equation. And this -1 factor satisfies classical mechanics in the limit of no motion. And m0 is the mass of the body at rest. And if you take this and you expand it in a binomial series, you get this here, where this is the key result, being that an object has an energy even if it's in rest, an intrinsic energy, in that this rest mass is equivalent to an energy of this body. And it also implies that every other type of energy that you add to the body is actually equivalent to mass. And so you get the notion of relativistic mass, where an object, if it's accelerating, its mass starts increasing. And of course, it also, shouldn't click here, gives rise to the idea of the atomic bomb. If per kilogram uranium, if you get a certain, if you extract some of the potential energy out of this, you get, you can create a very destructive or very energetic device. Let's say with the peaceful stuff, you can build a very good power source. And the more of this internal energy of a molecule you can convert, of course, the more energy you get out of it. Now, uranium, this would be just burning something, so you release some of the bond energy of the molecules, which also manifests itself as mass. Uranium, you have fission, so you get bond energy between atoms. Deuterium, that would be for fusion. So again, that is you can only do that for specific atoms where the energy difference is such that you get some energy out of it after you fuse the atoms. And antimatter, of course, would be the complete conversion of the rest mass itself into energy, which is one of the most efficient processes. Very desirable, but haven't been able to do it yet. Now, when we move to general relativity, I like to start with this statement that gravity is not real. And the first time I heard about that, it took me some time to wrap my head around this, that in the context of general relativity, you can basically treat gravity as a fictitious force the same way you would with the centripetal force or the Coriolis force. It only exists in a frame of reference that is subject to a space-time distortion. If space-time is flat, there would be no gravity. So this has been discussed at length because it was a huge conflict with Newton's picture of the universe. He would say gravity is the force of attraction between two bodies. And then when we get to general relativity, the idea is that gravity is just a manifestation of space-time curvature. And then we can say gravity is a fictitious force because in this context, you can look at us staying on the surface of the Earth, not as a result of a force acting on us, but as the fact that the Earth's surface is constantly accelerating towards us, which is, when I've heard it for the first time, was pretty mind-boggling. I think this is one of the most interesting outcomes of these theories. General relativity, again, this has been one of the most successful theory to explain the motion of macroscopic objects in the universe. It predicted successfully the precession effect that we see in stars moving around black holes, something that Newtonian mechanics is not able to predict. And you can see this here in a nice little simulation. And it also predicted gravitational waves, which only recently we started to observe, and where the implications and potential for research is not completed by any means. All right. So to give you an idea, again, this is not necessary to talk about some of the propulsion concepts, but to give you an idea of the different concepts that go into general relativity, and maybe also so you can look at stuff that people present to you and you have a better understanding what they talk about. The general relativity, when we replace Newton's gravity or Newton's laws of motion, we need the Einstein field equation. And this is a continuous field theory. What is important in this equation here is that you have geometry of space-time encoded in this term. You have a metric which describes how you would move along this space-time. And you have an energy momentum tensor. And this whole term on the right-hand side here describes the mass and energy distribution that gives rise to the geometry of space-time and the way that you have, or the way that the space-time interval is curved on this space-time. So this is where the equivalence between space-time curvature and the distribution from energy and momentum comes from. All right, so now we have some basics. I'm going to move into application to space propulsion. And I want to start with one that is actually being tested, and it's called the Mach effect thruster. Although now I think a lot of people would call the specific effect that is used to produce thrust the Woodward effect, after the person who is currently performing most of the research on it. And the Mach effect is originally tied to a problem that still has not been solved. And that is, so we have a rest mass, and we have inertia in the Einstein field equations, and they do stuff. We can describe what they do, but the underlying question of how does the inertia actually arise is not solved. If all motion is relative, then how is it possible that we have any kind of absolute inertia? And so Mach's principle basically says the inertia comes from the interaction of a body with the mass distribution of the entire rest of the universe. Now, this is a lot to swallow, and there's a lot of, I would say, discussion still going on, because to make this work theoretically, you have to rely on stuff like gravitational absorber theory and advanced waves, which is still active fields of research and where the last words have not been spoken. So especially with advanced waves, this is a topic of discussion that's not settled. But if you accept that Mach's principle is true, so that the inertia of one body arises due to its interaction with the mass in the rest of the universe, you can write out a gravitational potential equation, which is here the first one, in which you have higher order terms. So this first one here, this 4 pi g rho 0, would be corresponding to your rest mass, influencing the gravitational potential. And then on the right-hand side, you have higher order terms, where fluctuations in an object's energy can introduce fluctuations in the gravitational potential, or vice versa, fluctuations in the object's mass. And if we neglect this first term here because it's low order and usually very small, and you integrate it over a power cycle of some device, you can actually write an equation like this, where you have a delta in rest mass equal to negative some constant times the time change in power. So if you imagine, for example, a piezoelectric device, where you can increase the energy content of the device by applying voltage, and if this is a sinusoidal voltage, then this would imply that the rest mass of the object is changing as the power input to the piezoelectric device is changing. And this effect is orders of magnitude larger than what the very familiar E equals mc squared would suggest. And this is exactly what Mach effect thrusters are trying to use. They're trying to use this effect by combining a reaction mass with a piezoelectric actuator and a moving mass to rectify the sinusoidal effect into a directed thrust. So here on the top, you see a nice little sketch of what this would look like. So you have the PCT elements, you have the electrodes in between, you have a reaction mass that is mounted here and a mass that is free. And if you set this up correctly, the idea is that you can rectify this, this alternating thrust into a directed thrust. This is a very interesting idea because it would enable propellantless propulsion, since all you need is an electric generator on board of your spaceship and this kind of device. And it has been tested quite a bit with different results, so it's not conclusively proven that it actually works. And the governing physics is not entirely settled. So there's a lot of discussion going on about this. There's further tests currently financed by NIAC, if I'm not mistaken, the NASA Innovative Advanced Concepts program. So there might be some interesting results coming out of that in the future. And if this works, of course, then this would also indicate that the underlying physics might be correct, which has huge implications for a fundamental understanding of the universe. And give you an idea why this propellant at spaceflight is actually such a big deal. If you look at the different space vehicles that we're using or that we have used, you look at the takeoff mass, which goes into the millions of kilograms in some cases, and you look at their payload fraction. So a lot of you can say 95% of the spaceship or 92% of the spaceship is propellant. So if we can come up with a device that allows us to perform propellantless propulsion, this would be a huge deal, because we could go much further with much smaller spacecraft, or we can use the mass for life support systems, radiation shielding, or just for more payload. So this would be a huge deal if it actually works out. Of course, this kind of technology is, in a sense, well, it's not too crazy with regard to the actual velocities that you can get. You're still moving at sub-light speeds. But one of the, I guess, most interesting implications of the theory of relativity is that there is actually ideas coming out of this to enable faster than light travel. So we know, on the one side, we know that nothing should be able to go faster than the speed of light. But we also have heard of probably a million concepts that propose exactly that. How can we manipulate the physics that we know to still do it, to go around this limit of the speed of light? And there's a couple different concepts that I've listed out here, like we could slow down the light and then just go back and then try to fly at the original light limit. Is kind of useless, because then we're not actually faster than the speed of light. Maybe there's something in quantum mechanics that would allow us to do this. There's the idea of hyperspace travel, going to a higher dimension, where for a given distance we travel much further in our three-dimensional space. And the one that has, I guess, garnered the most attention, and that it seems at the moment the most realistic, although it's still very distant, is the Alcubierre warp drive. So I'm going to talk a little bit more about this. And this has also been mentioned in the last talk by Olivia. So I'm going to go a little bit more into the details of the physics. So the key to solving the Einstein equations and come up with something useful is to find the metric. And this is notoriously difficult, but it has been done in a bunch of cases. So Alcubierre came up with this idea of, well, if I can't go faster than the speed of light in vacuum, what if I just contract space-time in front of my ship and expand it in the back? And so locally, I'm never faster than the speed of light, but I can make this contraction so fast that I'm globally going faster than the speed of light. So you're not breaking any laws locally, but globally you would. And so you would create a warp bubble, where this is kind of a hyperspace embedding diagram that shows what this would look like if you contract space-time in front of a spaceship and expand it behind it. And once you have this metric, you can calculate what kind of matter distribution do I need. If you remember this T00 that was in the energy mass tensor. And so you can calculate the matter distribution needed to get this kind of warp bubble. It's very practical in a sense. The problem then arises from this negative sign, because it tells you to create this kind of bubble, you need a negative energy density or a negative mass. And this is also called exotic mass. And the initial results of Alcubierre indicated that you would need a more negative mass than there is in the universe. So initially it's like, okay, this is interesting, but kind of useless. And people started to play with it a little bit more, and they realized if they give the distribution of matter a certain shape, like this kind of donut shape here, and then start pulsing the width of this donut, they can actually reduce the amount of matter needed to a couple Jupiter masses, which is still outrageous, but compared to the entire mass in the universe, it's a It's a nice improvement. And then they came up with these nice renderings. That's, of course, always very inspiring to look at. And I thought this is interesting because the shape of this spacecraft with these toroid structures is actually derived from the solutions of the Einstein field equation, where they say we need to minimize the mass, we need a toroidal distribution of this negative energy or mass, and we hopefully can pulse it in some way. And in that way, we can create a spacecraft that is able of building such an Alcubierre warp bubble and going globally faster than the speed of light. Now, of course, you can already guess that this leads to some complications. As we've seen in the space-time diagram earlier, that when we move faster than the speed of light, we move into this non-defined space where there's causal disconnections. So cause and effect become a little wobbly, and you're also disconnected from the other observers in the universe. And to illustrate this, there's this nice simulation that I found on YouTube. And on the top, if you would be, let's say you're on the moon and you look at Earth and you have a spaceship going by at 1.5 times the speed of light, that's on the top. And on the bottom, you have the same spaceship also again moving at 1.5 times the speed of light, but this time with an Alcubierre warp drive. And it's going to look weird. So you can see when the spaceship occurs on the top, I'm going back a little bit. When it occurs on the top, it's actually two spaceships that split up, heavily distorted. One moves to the left, one moves to the right. The one moving to the right becomes more circular, and then as it moves past the Earth, or out of our field of vision, it starts stretching again. On the bottom, where we have an Alcubierre warp drive with a warp bubble, you see this weird visual distortion. Again, the two spacecraft, the visual distortion persists. The spacecraft keeps moving until it goes towards the edge of our field of view. And then eventually the visual distortion seems to disappear, and it moves out of our field of vision. And the reason for this to occur is that, well, on the top, if we think back to our space-time diagrams, if we move faster than the speed of light, then the spacecraft is outracing its own photons, which means once its relative velocity to the observer is so low that we can actually see it, we will get photons from two directions. We will get photons from the spacecraft with a relative velocity below the speed of light, and we will get the old photons that the spacecraft outraced, and we suddenly see two spacecraft. We can still tell that the spacecraft is moving properly into the future, but it's a very strange way of looking. It's a very strange effect that occurs there. And then when we have the Alcubierre warp drive, we get these additional distortions due to the gravitational lensing effect of the space-time distortion that we created in front and behind the spacecraft. Everything else is the same as above, where the reason that we see initially two spacecraft is that the spacecraft is outracing its own photons. And then as it's right in front of us, so its radial velocity is way below the speed of light, but then as it's moving out of our field of view and its radial velocity starts increasing again towards the speed of light, it starts stretching because of the space and time dilation effects that we talked about earlier. So we saw visually that there might be some issues with moving faster than the speed of light, even if we could do it. And there's more issues that are worth thinking about. So we have causal and energy condition violations. Energy condition is we need negative energy to do this. Causal violations because technically, if you do this, because you're outracing your own photons, it would be possible for the spaceship image to arrive in the past before it was actually launched, which should not be possible. It's kind of mind-boggling, but this is what all of the physics implies. Then navigation of the spacecraft would be very difficult because you have a causal disconnection between interior and the exterior of the bubble. Nothing on the interior can reach the exterior. And on the interior, everything you look at, because you're moving faster than the speed of light, everything coming towards you is infinitely shifted into the UV. So it's becoming X-rays, gamma rays. And behind you, everything is infinitely shifted into the infrared. So you cannot see anything there either. There's also the problem that once you actually hit the speed of light, there's the possibility of a very strong beam of Hawking radiation disintegrating you. So you're actually not going anywhere. So that would be a quantum effect preventing you from going faster than the speed of light. We just don't know if that's going to happen. And then there's the possibility that once you decelerate, there is a release of a massive amount of energy in front of the ship, which could disintegrate your target location. So you want to go to a nice tropical planet. You get there, disintegrate the planet. It's a little unlucky. You have to go somewhere else, maybe park parallel this time. And of course, you have time dilation, where even if you fly in this type of spacecraft for 2 years, by the time you reach your target, everybody you know back home would already be dead. I think that's a very kind of famous implication, but I wanted to just bring it up. So these are some very interesting things that can happen when you're trying to break the light barrier. With regard to producing negative mass or energy, this is being actively discussed if that's actually possible, because it has been observed, and there's some physics that in principle says, yeah, it is possible in principle. We're just not sure if we've ever observed it. So one would be from Hawking radiation. We know that the particle pairs that are created on the edge of a black hole, one of them should be positive, one of them should be negative. The positive part is released. That's what we observe as Hawking radiation, or would observe. And the part that stays is the negative part. So if we could somehow finagle that negative part out of the black hole, we would have negative mass or energy. Then there's the Casimir effect, which is illustrated here on the right, where you have two plates very, very close together. So you're restricting the wavelengths that are possible to exist in between this space. And due to this restriction, you're creating a negative energy density compared to the surrounding vacuum. So you can see here on the right, you have a much richer zoo of waves or of quantum fluctuations here on the right in the vacuum, whereas inside of the cavity, you're restricted to waves that correspond to multiples of the length of this cavity, and that creates this negative energy relative to the surrounding vacuum, which we might be able to utilize in this type of in a faster than light application. There's also a concept called squeezed light, where the quantum uncertainty of the squeezed state is lower than that of a coherent state. So relative to the coherent state, you're in a negative energy state. It's a little questionable if that is really giving us negative energy or mass in the way we would need it. And then finally, there's the idea that an exotic bare mass of electrons could give us negative mass. This has also been discussed by Woodward a lot. And yeah, it's speculative, but it's an idea. So I just wanted to put it out there. Now, instead of building our own like space-time distortion machines, we can also think of maybe trying to utilize something that already occurs naturally, in this case, black holes. So a black hole, just as a reminder, is created when you have a collapse of a massive stellar object. The gravitational pull becomes so strong that it overcomes the pressure as the stellar object collapses, and eventually the gravitational or the space-time distortion created by this concentration of mass and energy becomes so strong that we create what we call a singularity, a point where the Einstein field equations break down. And as far as we know, nothing beyond a certain point around the black hole has any bearing on the observer. Outside it, time seems to freeze for an outside observer. And as far as we know, this is the most efficient compression of mass into a region that exists. That seems maybe a little like an arbitrary point, but if you're interested in extracting energy out of something, it's actually very important, because then specific energy of something is of interest. There's a couple different types of black holes, and two of the more important ones are static or Schwarzschild black holes and rotating or Kerr black holes. Schwarzschild and Kerr are the two people that found the solutions that describe these kind of black holes to the Einstein field equations. Now, what Einstein and Rosen noticed was if they take the Schwarzschild metric for a static black hole and they just extend it to infinity to get rid of the singularity, then suddenly we are connecting two different regions of space and maybe even of different dimensions. And they called now what we call this often is a wormhole. And we think of it as a shortcut through our universe. So that's illustrated in the bottom. If you have a two-dimensional sheet, this idea of folding it over and just poking a hole through it. So this is the idea of extending the Schwarzschild metric to infinity, get rid of the singularity, and you can travel a much shorter distance through the wormhole than you would if you would just stay in your regular space-time. Of course, it's not that easy, as you can probably imagine. You need, if you want to actually travel through a wormhole, you would need to avoid the singularity that's there, and the strong tidal forces that are acting on the inside. You would need to avoid the event horizon, and you would need time to traverse the wormhole. And one of the first things that they noticed when they looked at this closer is that a wormhole in principle can form every time a black hole is created, but the pinch off of the throat here is so fast that not even light can travel through it. And to stabilize this kind of wormhole, again, we would need a lot of exotic matter with negative energy density. So we're back to the same problem. So showing you this because I thought it's kind of neat to illustrate what it looks like to go through a wormhole. So here you're on, let's say, our side of a wormhole. On the other side is a different stellar system. And you can see this distortion here is due to the space-time curvature at the mouth of the wormhole as it moves inwards, so to say. But of course, in a three-dimensional space, it's a little hard to illustrate. And the interesting thing is that if you could make this work, you would probably just go through. You come closer and closer to the wormhole. You step through. There's nothing you would notice if there's no strong tidal forces and you can avoid the singularity. You just come out on the other side and hopefully saved a lot of time to do that. And another interesting implication of wormholes is that if something like this would be possible, you could also turn it into a time machine. And while this is a very interesting idea, this is also one of the main reasons why a lot of physicists think that this is, in the end, it's not going to be possible to construct something like this. Something in quantum mechanics is going to prevent us from building wormholes, whether that be a pileup of energy that destroys the black hole or the wormhole, or it could be that that the singularity and the quantum fluctuations that are associated with are such that they would always pinch off the wormhole. They think that something will prevent us from building this, but of course that doesn't stop people to think about it because it's an absolutely fascinating prospect, exploring the edge of what we understand and maybe coming up with really far outlying solutions to some of the propulsion issues that we have, and maybe issues of knowing the lottery numbers from last week and going back and putting them back in. All right, so something that might be a little bit more practical, but not by much, is called a black hole bomb, because for something like this, we would not have to build a wormhole, we would not have to change an existing black hole. All we would have to do is find the black hole that is spinning. And so if a black hole spins, it starts dragging space-time around it. So you have an event horizon. It's illustrated down here. The black part, event horizon, is where nothing can escape. But around this event horizon, you have swirling space-time, and this is called the ergosphere. And by something called the Penrose process, after Penrose, who came up with this idea, you can extract energy or work from this rotating part of space-time. And This is also called super radiant scattering because you usually want to do this with a beam of light. Illustrate this here. So you would construct a reflecting surface around the black hole. You know, this sounds very simple so far. Put a perfectly reflecting surface around an entire black hole, and you would shoot a coherent beam of light into it, a laser. And of course, you would have to hit the ergosphere so that the light always can just escape the black hole. It can never go into the event horizon. And then it becomes, in principle, very similar to a planetary slingshot or a gravity assist maneuver, where the spinning of the space-time imparts some of its energy on the light, and the light carries it with it. And so as the light is reflected and bounces around, inside it becomes more and more energetic. And, well, it's called a black hole bomb. You can do this until you hit the super radiant instability. And this would probably be one of the most devastating devices you could think of on a stellar level. Or if we want to stick with the peaceful application, which is where I'm hoping this is going, then at some point you open the reflective enclosure and you extract part of the scattered light that has now been energized by the swirling space-time, and you use the additional energy from that to power any other devices that you might have. And in principle, this goes beyond harvesting the energy of an entire star. So you might be familiar with the idea of a Dyson sphere or Dyson dots. Robert Kennedy, if he's in the call. Where you try to extract the entire power of a star by building a sphere around it. This would be even more powerful. Powerful in the sense that you would have even more energy available for an even longer period of time. Another way of extracting work from black hole would be to try and capture Hawking radiation. In that case, we would basically try to capture the energy in the same way we capture other types of radiation through antennas, resonators, converter cells, as in the case of solar radiation. And you could use that as a basis for propulsion devices. Actually, a couple years ago, I4S came up with a concept like this, where the idea was to create very, very, very small black holes in a particle collider that's shown here as a ring, and then use the Hawking radiation from those tiny black holes as they evaporate to power a starship. Now, there's a lot of problems there with quantum mechanics, because when you go down to these kind of timescales here, and the required energies needed to do something like that, then it's not really clear if we would get even a black hole, if this would even be possible. But again, it's an interesting idea and an interesting concept to try and push what we know about the physical world. And yeah, I just want to leave you with these conclusions that the theory of relativity, or our knowledge of unified space-time, has taught us a lot about the universe. There's a lot of potential for breakthroughs still, because some parts of the connection between relativity and quantum mechanics, or the origin of inertia, is not clear, and there might be a lot that's coming out of that. But you have to be careful with concepts presented to you, because a lot of them suffer exactly from the same issues, that the underlying physics is not well understood, that they rest on a very specific interpretation of the physics, or that sometimes it's wishful thinking and that some of the numbers just don't work out. But again, it's very useful to stretch your imagination and try and come up with engineering solutions on the edge of our fundamental understanding. And yeah, I hope that maybe we can have a little bit of a discussion about this now.
Okay, thank you very much, Dan. That's a excellent whiz through. You're very prompt. That's brilliant. I'll just mention to everyone, if anyone's wondering, we've got time for questions and answers, but Dan does have to leave at the top of the hour. He's in Texas at the moment. Got to dash off to his lab to sort things out there. But he can take questions for the next 10 minutes or so. If anyone from the floor has got questions, I see there's a couple in the chat, Dan. I don't know if you saw that.
Oh, no, I didn't.
There's one from Patrick. One from Patrick asking that slide with the 1.5C spacecraft going past Earth, whether that's just purely a visual effect.
It is primarily a visual effect, but if you would get caught in the too close to the bubble where you have strong tidal forces, then of course that would be an issue for you. So there is the danger of physical damage if you would get too close. And of course, again, once the spaceship decelerates, there's a chance of a massive energy blast being released from the warp bubble disintegrating. And that also could cause real physical damage.
Okay, I think Detlef in the chat also mentioned that there'd be, obviously if you move too close to the Earth, there would be likely be damage. That's what you're suggesting. So the huge gravitational forces.
Yes, yeah, they would be highly localized. So you can localize these strong effects very, very much. But yeah, it is an issue. What's the reasons?
I think you may have answered that one, but have a read through that. It's about using Hawking radiation.
Oh yeah, so this is really interesting. Yeah, so recently there's been a lot of progress with analog black holes in labs. So analog black holes meaning using fluid dynamics, using optical mechanisms, even with acoustic devices, to build something that resembles black holes in its properties. So I'm very glad that was brought up. You should definitely look into this, because this is something we can build in labs and investigate. And I have not read that paper, but I definitely will, because those analog black holes, they potentially allow us to investigate the nature of those virtual particles better. And if we can manipulate this in any way, then yes, we might be able to extract very exotic properties out of that.
Okay, excellent. I see that John has got his hand up, so if you'd like to unmute yourself, John, and ask your question, go ahead.
Hi, Dan. It was a fun talk. UT physics back in the 80s, but so anyhow, yeah, my question, it kind of relates to both the Mach effect and the Alcubierre. And in both of those, I mean, I've looked at them and I have a hard time kind of with both of them. And what it is if you envision a large volume with either a Alcubierre or a Mach effect in the center of it, asymptotically, I'm kind of flat in both of those cases. And, the Mach effect thruster, I kind of envision it as I've got a power supply and the device, and I could sort of think of it as, transfer of fluid or, pumping something back and forth between the two pieces, the power supply and the device. So asymptotically, I don't see any mass change. Locally, on one side, the mass is going up and down. So how that's going to move anywhere relative to the distant stars, I don't get. And Alcubierre is sort of similar in that I'm assembling the device, and asymptotically, the metric's flat. Say I'm halfway between here and Alpha Centauri. You turn that on, that ripple in the metric is still going to move like a gravity wave, right? And propagate at c. So I still don't see how you end up, with moving from here to there at a any kind of superluminal velocity. So anyhow,
yeah. So those are very good points. So to the Mach effect, I can say something real quick. I think I forgot to say that specifically, because this is very much connected to the manipulation of inertia. These higher order terms only come in when you have acceleration present. So the idea would be in this case that the power generator or your battery that is pumping energy out or in is not affected by the Mach effect or Woodward effect, because it is not accelerated at the right phase relative to the change in the internal energy. Whereas for the Mach effect, for the thruster device, that's why you have those piezoelectrics that are expanding and contracting, you provide an acceleration at in the right phase with the change in internal energy to actually generate the mass fluctuation. So that's how I think that is the justification that is usually given for why it would work and why it would not be nullified by a battery or the generator itself. For the Alcubierre drive, so if I can get that correctly, there is a difference between the ripple that you're creating for the Alcubierre bubble and a gravity wave. And that difference is what essentially the idea is, that you're moving the ripple. Yeah, so the gravitational wave is not a contraction and expansion of space-time, whereas the Alcubierre drive specifically does that to globally get you above the speed of light, but locally keep you below it. So as far as I understand, a gravitational wave is not a contraction or expansion of space-time in the same way that the Alcubierre bubble would be. But I mean, I'm happy to if you can extend on that a little bit more. I'm happy to talk about that.
Yeah, I mean, I've looked at it multiple times, and I've just never been able to quite convince myself that there was anything that would, come out faster than the speed of light. It always seemed to me like the argument that it was the expansion and contraction of space seemed like a hand waving kind of an argument that I never really, was able to get to the bottom of. I've crawled through Alcubierre's paper multiple times without really buying it, and and then people have kind of taken it and run with it, but at the very bottom of the argument, it just doesn't seem to, I just can't figure, get my head around it in any way that, I believe it just, if you're perturbing the metric, I mean, first order, the linearized gravity that they use for the gravitational wave equations, basically start with here's a metric, here's deltas to the metric, and they always come out propagating at c, and the only place anybody points to where things are moving faster than c is back during the inflationary stage of the early universe, and and the underlying physics, I think, of what drives that inflation is still an open question. They, I think, postulate fields that have never been observed in an accelerator or anything like that. So it kind of fits the observation, but there hasn't been any kind of laboratory demonstration of the physics going on in the inflationary stage of the universe. And I'd be pretty leery about turning inflation on somewhere locally in the universe and hoping that I can turn it off again somewhat later. So
yeah, that's a very good point. I mean, it goes exactly to this issue of all of this being somewhat speculative. I cannot give you a satisfying answer. This is something I would have to look at myself closer, but I'm going to keep that in mind for the future, because it's a very good point.
Yeah, I mean, I think wormholes are a little bit more interesting, and they certainly have some problems there. Lately in my my day job is an engineering physicist, but my spare time, like to ponder the fundamentals in that. And I've been poking around at a paper by Wheeler back in the early '60s, where he was looking at wormholes as a method of trapping field lines for fundamental particles. And these large-scale wormholes, I might as well try to build a black hole. I think they're just about as difficult. But we worry about the singularity at the heart of a black hole, while every single electron is a singularity unto its own. And the idea that the core of this paper of Wheeler back in the early 60s is that the bottom of an electron is actually the mouth of a wormhole, and the matter and antimatter is either the field lines going into a wormhole mouth or exiting, and that kind of ties in with some of the stuff that's been going on lately with the I want to get the words right, the quantum correlation in the the delayed choice type of experiments and that, where for what they're doing in the core of quantum computing.
Dan and John, can I jump in there? Just jump in there quick, because I think some of these very interesting things at the edge of known physics are really interesting, and we probably should be down the pub discussing some of them in more detail. And I'm very wary that you've only got a couple more minutes to go, so I wonder if David has got his hand up. David feels he wants to ask his final question, then maybe you can get off to your lab to sort out the waterworks, whatever it is. David.
Okay. Yeah.
Thanks, Rob. The digital hand appears. Besides the thing in the Bible. Anyway, hey Dan, nice presentation. Thank you. I got distracted because I got into what something John said, and I'm thinking about the next thing we should explore is called the inflation drive. A little bit scary. My original question was, you covered these types of drives here nicely, but they're all going to be a little bit inefficient, and whether that appears as pulses of exotic particles or ripples in gravitational energy or with a Mach drive, just electromagnetic things. It seems like a nice opportunity to do SETI research. So if you come across anything like that, that's got a characteristic frequency or characteristic chirp or something like that, might be a nice thing to think about. Anyway, thanks.
Yeah.
Thank you, Ron. Thanks.
Yeah, thank you. I actually never thought about that. That's a very good point. I mean, I mentioned this earlier, like the research in gravitational wave astronomy is, I think, only in its infancy. So it might be that we come across some very new things there that we have not expected. And of course, it's a very good point that we should always look out for other intelligence in the signal. Usually we can find a natural explanation, but that's an interesting prospect. Okay, so there's one more question from Patrick
in the chat.
Well, I'm not sure. From my perspective, it does seem like we're getting slowly to a point where the unreconcilable differences in different fields are starting to pile up a little bit. Then again, a lot of developments in fields are also so deep and specialized that it's very hard to even hear about them if you're not really in the field. I personally don't like saying that we need another Einstein, because yes, Einstein definitely was a great mind, but he also, the reason he was able to do what he did was because there was so much work done before him, and he was in the right position to take all of that and put his own mind to build something out of it. And I think that's how we should keep looking at it, meaning that everybody should make as much contribution as possible. And then hopefully somebody will eventually be in the right position to put it all together for the next step.
Okay.
John has I might have to sign off after this, but before you say your thing, I just want to say thank you all for attending and listening, and I hope you enjoyed it. And
okay.
Go ahead, John.
Yeah, no, just with regards to the Einstein, actually what I'd like to see is another pair of Wright brothers.
Okay.
They didn't have to invent new physics. They just figured out what was already there.
Yep.
Yeah, true.
Okay, I'll draw a close to the questions just now. I know Dan has got to shoot off, and I say thank you again, Dan, for that. Very interesting. It's all been recorded, and if like me, I might need to watch it again. I'll watch it again through the website. It'll be on there in a week or so's time when the guys can put the video together. But thanks again for that, Dan. I'm sure everyone will say thank you as well. And then
thank you for the opportunity.